Okay, so I think this is going to be my final video on this topic, sort of an appendix, and to just wrap up some of the loose ends. In my previous video, I showed everything you need to actually utilize this formula, and it is a full-blown analytical formula in the sense that, you can get as much precision as you need by calculating each term in a as a polynomial. Basically, you just truncate the series, you get a polynomial that gives you the critical t value to some precision. If you need more precision, you calculate more terms. But I wanted to do this video. It's just three extra pages. I wanted to show sort of in practice how you do some of these calculations. It's really easy once you realize what's going on, and then just add some extra stuff. So I'm going to start just zooming in on different parts of this page. We have the critical t-value definition, and you parameterize that according to ATA, which reflects the confidence level you desire, and then V, or the degrees of freedom that you have that you're looking for. And the important thing about this equation was singling out that U term because the bulk of the computation is in that U term. And again, we talked about this in the previous video. But basically, we found that this method and Domenici's method, they're equivalent, and you can express that U term as an infinite series parameterized by the gamma term. The gamma term being this beta function times this confidence interval function. And we also showed that, the most important part of this infinite expansion was to calculate the coefficients. The coefficients themselves are sums of these partial Bell polynomials, and the entries of those partial Bell polynomials, these f functions, that I'm calling them f functions, f sub L, I show over here. This first term, the 1/2 times 1 plus -1 raised to L plus 1 times -1, L minus 1 over 2. That term really is just going to give you a 0 where you need it. It's going to give you a -1 where you need it, and a +1 where you need it. And I demonstrate that with the examples. So for example, if you want f of 3, you can see you just plug in 3, and it comes out to that f of 3 value, which was -2 times a. And then if you want the f of 5 value, you just plug in the 5, carry out the calculation, and that gives you that value you want, the 12 times a minus 1. And again, that a value is related to the degrees of freedom, v, as v over 2 minus 1. So it's just a linear function in v. And I just also wanted to note the definition of the following factorial, which, if you have a raised to k following factorial, that's just going to be a product of the a terms, and you subtract off 1 sort of every time up to a k value, subtracting off k. So you can see I calculate here a couple of these f sub L terms. F sub 3, that gives you -2 times a, which means that the second entry in the partial Bell polynomial is going to be -2 times a, all divided by 3. And you can see I calculate these terms out, the f5 value, f7, f9, f11, f13, and you can calculate as many of those as you want. They have a really simple form, in fact. And you also notice that every other term is 0. The thing that's nice about that is it enables us to simplify the calculation immensely. And so partial Bell polynomials, which are already efficiently computable, in this form that they're given via the calculating the critical t-value, the computation is even more efficient. And so I just wanted to show that definition up to some number of terms, and I also want to show you how computing the triangle of coefficients from my previous videos actually gets you there. So for example, when you have this partial Bell polynomial representation where each of the entries corresponds to an x value, as I've sort of shown here, you can see that when you carry this out, this computation out, you're going to get what we got with the Dominici expansion. These interesting coefficients, you know, the 7 and 3 coefficient, the 127, 123, 30 coefficient, and that those coefficients sort of represent the triangle that the triangle that whose coefficients multiply the gamma term which you're expanding into. And I sort of show that, you know, depending on what term you're calculating, you're going to get sort of a gamma term raised to a power divided by a large number multiplied by these polynomials in A, the polynomials of which correspond to those values we calculate in the coefficients triangle. And I just want to show this. So I gave you some examples, but I also want to show you how simple this is. So for example, we're going to calculate n equals 3, we're going to calculate n equals 5 and n equals 7. And I'm just going to briefly skim over, and you pause the video if you want to look at it in a more detailed way. The algebra seems to be correct. There may be a mistake, just caveating here, but the numbers all come out the correct way at the end. So with n equals 3, we're going to calculate that term. That term is going to look like this, right? It's going to be the g sub n term times 1/2 raised to the third power times gamma to the third divided by 3 factorial. So each of the terms is going to have that form, and the bulk of the computation is going to be encapsulated in these coefficient terms, these g sub n terms. So you're going to pull out all that stuff in the front and just use the formula to calculate these g sub n terms. And here we're going to take the sum from 1 to 1, because if you go back up to the formula, that sum goes from 1 to 1 when we choose n equals 3, because 3 minus 1 is 2, divided by 2 is 1. A sum 1 from 1 is just going to be the term, which means our term is going to be -1 raised to the 1 times 3 to the 1 rising factorial times the partial Bell polynomial 2 sub 1. And we recall that every time you have a partial Bell polynomial be n of 1, you're just going to get the x sub n entry of that Bell polynomial. So here we're going to get the x sub 2 entry of that Bell polynomial, which turns out to be f3 divided by f sub 3 divided by 3. So we're going to get this form here for the n equals 3 term, recalling that every other term is 0. The f sub 3 term then is going to be, here I'm showing the algebra, it's going to be this. You carry out the algebra. I'm doing it very tediously and just showing, you know, as I go across. And ultimately you're going to get 2 factorial divided by 8 divided by 6, which is 1 divided by 24. And so then you can see, indeed, that method exactly equals what we expect to see here. And then n equals 5, same story, just a little bit more involved. And once you get the idea, these become extremely easy to calculate as long as you have as long as you are comfortable with calculating Bell polynomials. And there's a lot of literature on calculating partial Bell polynomials, so I can't really get into all that here. So here, again, you've got the work is really in calculating this g sub 5 term. If you take 5 minus 1 divided by 2, that's going to give you 2, which means your sum is going to run from k equals 1 to k equals 2, which means your partial Bell polynomials are going to be b sub 4 of 1 and b sub 4 of 2. And so I show here that you do the calculation. The moderate difficulty is in calculating these partial Bell polynomials. But you can look at the table, realizing that anyway, you can look at the table and just do some simplifications. You can see it all kind of works out in the end. At the end, you're going to get sort of a coefficient multiplying a polynomial in a terms. Usually there's a number that factors out. In this case, that number is 4 that factors out, which gives you the coefficients 7 and 3, which matches what we got with the Dominici expansion. And then just for completeness, I wanted to show how you do this for n equals 7 as well. And I'll just briefly skim over this. Pause the video if you want to do the algebra yourself. But it's all here. So again, the sum runs from k equals 1 to 7 minus 1 divided by 2, which equals 3 when you choose n equals 7. That means you're going to have 3 partial Bell polynomials to compute. And again, I just run through the sum. Follow along. And then here's more of the algebra. There's a lot of simplifications that happen, lots of cancellations, lots of interesting things that you could really dive in on if you if you were looking for, more improvements. But as you can see, at the end of the day, what you get is simply, again, a polynomial in A whose coefficients match the coefficients we computed in our triangle, those Dominici coefficients, 127, 123, 30. Which means, when you put it all together, you're going to get this answer, right, for that n equals 7 term. So I just wanted to show how you get there. And then moving on a bit, you can see how that triangle gives rise to the expansion, right? And that means that if you compute the triangle of coefficients, you can increase the precision as much as you'd like. So initially we had only computed, 4 terms basically corresponding to n equals, going all the way up to n equals 7. And this is the polynomial you get. And then I just wanted to show, you could stop there. You could express your result as this really large polynomial, and it does give pretty good precision, which I'll explain later, up to a decent number of terms. But there's additional structure here. This is just a kind of an additional thing that's interesting, that's useful. There's some additional structure here that can be exploited. You realize in these the polynomials that come out as the coefficients, or excuse me, I should say it the other way around. The coefficients that come out as polynomials, the leading term and the last term of those polynomials represent the ends of the triangle. What's fascinating, if you study math a lot, sometimes certain sequences pop out and you automatically realize where they're from. And in this case, is this is exactly what happened with me. So you can actually realize fairly quickly that, these end terms have structure on their own. And so if we express this polynomial, or excuse me, if we express this expansion in terms of many, many of these terms, going up to, I think let's see, let's count. Let's say I've got 1, 2, 3, 4, 5, 6, 7. This is 7 terms. You start to see additional structure. And what's interesting is you can actually group different parts of this in interesting ways. And that's what I do. That's what I do below, is that I actually notice that, okay, I'm going to pull out those leading terms, group them on their own. I'm going to pull out those end terms, group those on their own. And maybe I should say, quickly that these these terms that I'm calling A, they're the green terms, and then the terms that I'm calling B, those are the red terms in our triangle. But you can group these terms on their own and express these infinite sums as analytical forms. And in fact, I show up here how to solve for these two infinite sums, the A and the B. And in the A, you recognize that these terms are actually terms of the inverse error function. And you can see that if you type these into the online encyclopedia for integer sequences. But this sequence just immediately jumped out to me. I'm not going to do the proof. The proof is involved. It's kind of an accessory to this. But the inverse error function basically is the thing that's giving you those leading coefficients. And then, which means that you can sum up the largest terms of the coefficients of your expansion. You can sum them all the way to infinity. It's also nice that the end terms also have a nice analytical form. It's a little more involved, it's a little harder to find, and I show it here, but basically, the sequence 3, 30, 630, so on and so forth, that can be represented by this sequence, which is 2n plus 1 factorial divided by 2 raised to the n. If you start at n and you go to infinity, and then the denominator terms, the 960, the 8640 terms, so on and so forth, that can be expressed as this expression, 2n plus 1 factorial times 2n plus 1, if you start at n equals 2 and go to infinity. So to make these match up, obviously you have to decrement one of the two terms, which I do below. I show that this, sequence can be written simpler, and there's a lot of cancellation that occurs. You pull out some gamma terms. You're going to get this expression on the right. There's, you factor out the factorial term, and different parts of that cancel, which ends in giving us this infinite infinite sum, expressed as, some coefficient times the infinite sum from n equals 2 to infinity of gamma raised to 2n divided by 2 to the 2n multiplying, in brackets here, 2n squared plus n. And I'm not going to go through the derivation exactly of how to solve for that infinite sum, but it suffices to say when gamma is below 2, if you actually do solve the infinite sum, you're going to get a term that has this nice analytical form, which is 2 times gamma minus gamma times the natural logarithm of 1 minus gamma squared divided by 4 minus 4 times the inverse hyperbolic tangent of gamma divided by 2. All of that needs to be divided by gamma, and then from that you subtract off gamma squared divided by 12. And just for completeness, the reason you subtract off that last term is because that's the term that you get when n equals 1. And so doing the infinite sum is easier if you start it at n equals 1 and go to infinity. So that's sort of just for completeness. And so, it suffices to say, like, here we derive two analytical forms for these two infinite sums, the A term and then the B term. So that's pretty nice, and that means that if you want to find U, and I'll just zoom in here. Here are the analytical forms for that A and B term. So what's interesting about this, it means that if you want to find U, you don't have to actually start with compute just the complete polynomial. You can actually start with this A term and this B term. You can start with an approximation which uses these analytical functions. And so now the U term is actually going to be that A function plus that B function plus any of those middle terms, which I'll demonstrate here by just putting those in yellow, right? These are all these are going to be all those middle terms. And you can just tack on those middle terms if you need more and more and more precision, which I'm going to move on from here and explain how precise this is, explain some of the errors and stuff, because I did some computations. But basically, you can see that that green column is going to sum to infinity, and it's going to give you the A function. That B diagonal is going to sum to infinity, and that's going to give you this B function. And then if you want more precision, you just need to tack on the polynomial, the expansion terms that come from the yellow triangle. And that gives you more and more precision. Okay, so I thought that was a pretty neat result. Definitely something worth sharing. But now I wanted to show how precise this can actually be. Okay, so moving on from here, I decided I was going to do some computations just to see how precise this is. And here I've got a table. I'll zoom in onto my first table. Hopefully the compression quality on YouTube is not going to destroy this, but basically you can see, if your ATA, your confidence level is really low. In other words, you don't really need a lot of confidence. The function alone, just adding the A function and that B function that we derived, nominally, even for low values of the degrees of freedom, is going to give you precision in into the fourth decimal place. And as the number of degrees of freedom increases, just the function alone, this is that middle column I'm looking at, just that middle function alone, once you start getting into values of about, degrees of freedom of about 25, I mean, you're already you know, into the, into 5 or 6 decimal places of precision. So that is a nice feature and result, um, in the sense that, you know, here you've got this analytical function that is so precise. But what's nice is you can actually tack onto that function those middle terms to get even more precision. And in fact, when you start tacking on those, and this is the right column I'm talking about. In fact, when you start tacking on those middle terms, and I tack on 12 additional terms, you get extreme precision. So, and again, this is with this is low confidence values or low degrees. This is for low confidence values. And so when you tack on those middle terms to get more and more precision, I use 12, plus I'm using those analytical functions I derived. You get precision into the, below 12 decimal places. You can see the error on the right here. And this represents at least one order of magnitude more precision than you can get with using just the polynomials themselves. So when you actually sum up the infinite series, you get about an order of magnitude precision more than just summing up, 15 terms of the polynomial. You can actually get more precision. And so I think this is a really nice result. And I need to also talk about um, what happens if you want more confidence. You want a higher confidence level. And I think the way I've explained this, that an ADA of 0.01 is going to give you about 98% confidence. Well, if you want more confidence for your critical t value, the errors are going to be a little bit larger, and you're going to need more terms in the expansion to reduce your error. But even still, the errors are not that unforgiving. In fact, just the function alone, once you start getting into higher degrees of freedom, you're talking about errors which are 7, 8, 10% um, off from the true value. Now, the one caveat here is the function alone doesn't give you a ton of precision for low values of degrees of freedom. And I'll explain that later, but that's just a caveat. But if you tack on to the function, if you tack on more terms, you can actually get pretty good precision right off the bat. I mean, even with only 3 degrees of freedom, that's 3 data points, right? You're getting about 25, 26% error. And that error rapidly diminishes. And if you compare it with the function alone, some of these errors are half or a third the amount from just having the function alone. And it's obvious it obviously represents a bigger improvement than just taking the polynomials, you know, term by term, 15 terms versus the function plus 12 terms. So you can see there's a lot of precision here that comes from this result. Okay, so the final thing I really want to talk about is one useful aspect of this, and then I want to talk about accuracy and precision and stuff. So one of the reasons I actually wanted to tackle this problem was because I wanted to figure out how sensitive the critical t value is to changes in the number of data points I have or the confidence level that I'm asking from any kind of statistical research. And ultimately, that comes down to computing derivatives of functions. And you really, and one way to do this, and so what I wanted was a function, a nice function I can calculate the derivatives to. And so here, I do calculate those derivatives. derivatives with respect to gamma, and a derivative with respect to A. And again, A is basically with respect to the degrees of freedom. It's a proxy for the degrees of freedom. So here you can see the partials of this function. They're relatively nice, but I just wanted to put them here for completeness. I need to back up a tiny bit. So you will remember, or you will recognize that I didn't compute the critical t values for degrees of freedom, when those degrees of freedom are like 1 or 2, and that's fine, because if you actually work through the math, a critical t value whose degrees of freedom are 1 or 2 is going to have a closed form that you can compute already. So I just didn't include them, just because Excel was being funny and it wouldn't give me nice values. So I guess I should mention that. Okay, so this is the last thing I want to talk about. I'll just zoom in here, and I'm just going to kind of read it. So my first point, because the expansion is taken with respect to increasing powers of gamma, the larger that your ADA is, and this ADA, remember, translates into critical values with lower confidence, this will allow for more accuracy. So the larger ADA is, which means lower confidence, that will mean you get larger accuracy. That means you need less and less terms to get a certain set amount of accuracy. And this is because a smaller ADA implies a slower convergence of that infinite sum. And the second bullet point, also, because of the interplay between gamma and A, both of which are parameterized by the degrees of freedom represented by V, an increase in degrees of freedom V will imply smaller values of gamma, though that will imply larger values of A. So you got to balance these two. In this regard, gamma decreases in size with increasing degrees of freedom V at a faster rate than A increases. A is just a linear function with respect to V. And generally speaking, as more terms are computed in the expansion, the difference in powers between the leading A term in the polynomial and the gamma term increases linearly in favor of the gamma term. So the smallness of the gamma term dominates the increasing size of the A term as more terms are added. And you can kind of show roughly that the nth term of the expansion, the size of that is roughly going to be on the order of A to some power times gamma of gamma to that same power plus n, where our A term is increasing linearly with increasing degrees of freedom V, but gamma is decreasing superlinearly. It's actually roughly exponentially. So that means that each term of the expansion, as you increase the number of terms, they're going to get smaller and smaller and smaller, which is good because that's what you want to see in a convergent series. And actually, I'll just draw this out real quick. Basically, what you're going to see, and I'll draw it right here. Basically, what you're going to see is, roughly speaking, as far as errors go, I'll just put, error at the top here. And then this is V for the degrees of freedom. Roughly what you're going to see with the errors is the errors are going to be very low for 1 and 2 because those have closed analytical forms. But it's going to rise in the middle, and this is due to the interplay of that gamma and A term. And then it's going to drop off exponentially as you increase the V. And that's just a general thing that you notice playing with these. Okay, so the other thing is, if you want infinite precision, one of the nice things you can do is use a formula like this to generate really close seed values that you can then use in another method like Monte Carlo or gradient descent. Although that's not exactly what I decided to do this for. But it does behoove me to say, this represents a great way to generate really close seed values, which is going to help speed up the convergence of any kind of Monte Carlo approximation or gradient descent approximation that you would want to do to get more and more and more precision, depending on how you're using this, if you don't want to calculate more terms of this expansion. Alrighty, so that's everything I kind of wanted to put in this video. Hopefully this helps some people. I remember when I was younger, taking statistics, the teacher never really explained why we had to use t-tables. And the answer, I guess, is that the analytical solution is just very complicated, and involves a lot of work, but it is possible. And hopefully over these last videos, I've been able to show that it is indeed possible and quite beautiful too. Some of the math is actually quite beautiful. All right, thanks for watching.